How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at temperature, reaction rate, and the Arrhenius Equation. So our objectives will be to explain the chemical reactions in terms of the collision model, interpret corresponding potential energy diagrams, and use the Arrhenius Equation. So let's get started. What is the collision model? So the core idea is molecules must collide in order to react. If you don't have collisions, you don't have a reaction. So if we can increase the rate of collisions, we can increase the rate of reaction. So concentration and temperature, what does that mean? Well, if we increase concentration, then we're going to increase collisions, which means we're going to increase the reaction rate. Temperature has two effects. So if we increase temperature, we have more collisions because things are moving faster. So if things are moving faster, it's like you got supercharged bumper cars, you're going to get a lot more bumping going on, right? So we also are going to have more reactants with enough energy. So just because they collide doesn't mean they're definitely going to react. They need enough energy to break the bonds that are there. So if you increase the temperature, more of those molecules have enough energy for that to happen. So we increase the reaction rate that way too. So not all collisions are effective. I kind of talked about that already, but effective collisions, it's a collision that results in a reaction, right? So it's just a fancy way of saying a collision that causes a reaction. So two factors affect whether or not a collision will be an effective collision. One, the orientation of the collision. Things need to collide in the right orientation. It's like shooting pool. They have to hit and collide at the right angle in order for you to have something happen. The second thing is there needs to be enough energy for the reaction. So the things, if they collide real weak, it's again like playing pool. If you barely touch the ball, you may not have given enough energy to go to the pocket. So it needs to have enough energy when it collides too. So let's take a look. I'll try to visualize some of this stuff. Colliding with the correct orientation. Colliding isn't enough for a reaction to occur. The molecules must collide with the right orientation for the reaction to proceed. So here I have a water molecule and I have an oxide ion. And if they were to collide, they may react, they may not react. If the oxygen ion collides with the molecule and it hits the oxygen atom of the molecule, nothing's going to happen. What this oxygen is looking to do, this oxide ion is looking to steal a hydrogen from that molecule. So if it bumps into the part of the molecule where there is no hydrogen, nothing's going to happen. Whereas if it comes in at an angle where it does collide with the hydrogen, hey, now we can have a reaction occur, and that oxide ion is going to steal a hydrogen from that water molecule. So you have to collide in the right orientation. The next thing is you have to collide with sufficient energy. If there isn't enough energy to break the bonds that are already there, you won't get a reaction. Right? So reactions where we're changing these bonds, we're breaking old ones and we're making new ones. If we don't have enough energy to break the old bonds, nothing's going to happen. So here comes the oxide ion in with barely any energy, real weak. It bumps in, but we don't get a reaction because there wasn't enough energy to break that bond. Whereas if this oxide ion came in with a lot of energy, bam, it's going to have enough energy to break the existing bond, and it's going to rip that hydrogen away, and it's going to make a new bond. Activation energy. So this energy required to initiate the reaction we call activation energy. It's how much energy has to go in for that reaction to occur. So we need a certain amount of energy in order to break that bond. So right now we have what we call the activated complex. So the collision occurred with enough energy that a reaction is going to proceed. And at this moment, there's a really high potential energy, right? So we have energy over there, reaction progression. Right at this point, we are at our highest amount of potential energy. We've collided, we're breaking those bonds before we make new ones. So high potential energy. So the next step will be for those bonds to break and new ones to be made. And that's when we end up at our final position, right? So that amount of energy from where we started as separate things to the highest peak where we got to get in order to get it to react is called the activation energy. Mathematic representation. So this is one of the uglier equations, in my opinion, that you'll have to deal with. So the rate law equation, we've seen rate equals K times the concentration of reactant A to some power, etc. So when we change the temperature or we add a catalyst, we change the reaction rate. But how? We haven't affected the concentrations of any of these things at all. So how is it that a rate is going to be able to change? Well, if this is all the same, if that's all the same, the only thing that could have changed is K. So K is what's changing when we alter these conditions. So the Arrhenius equation, here it is. K equals capital A times e to the negative EA over RT. So K, again, is that rate constant. A is a frequency factor, and it's basically how often are collisions occurring with the proper orientation. So it's measuring the collisions. EA is the activation energy, and it's basically how much energy is needed to get it to react. If you have a really high activation energy, the reaction rate is going to be lower or slower than if you had something with a really low activation energy. R is gas constant, and T is temperature. So temperature and rate constant. How does the temperature affect K? Well, we know that warmer temperatures will have reactions occur at a faster rate because things are moving around more. They have more energy, so more collisions will have enough energy, and there's going to be more of them. So again, if we take a look at this equation, how are we changing K? Well, we're going to make one equation for K at different temperatures. So let's take the natural log of both sides so we can get rid of that E thing. So we got ln of K equals negative EA, the activation energy, divided by RT plus ln of A. So that's just natural log of both sides. Now for different temperatures, T1 and T2, we'll have different Ks. We'll call them K1 and K2. So if we were to do a little math, we can subtract K2 from K1. So I do the same thing on both sides. So if I go, all right, hey, natural log of K1 minus natural log of K2, it's going to be equivalent to all of this for scenario 1 minus the same thing but for scenario 2. And that's why I've kind of color-coded them. So now we can do a little math. Now we combine and we can cancel things, and we end up with this equation. Natural log of K1 divided by K2, right? So when we subtract logs, it's the same thing as dividing the insides, equals EA over R times 1 over T2 minus T1. So that's just some algebra. You're probably not crazy interested in that, but this is the equation that we're going to be working with. So we can use this equation to determine what the activation energy is. We can also use it to solve for what a new K is going to be. So if we want the activation energy, basically we need to know the values for K at two different temperatures. So if we know K1 and K2 for T2 and T1, we can solve for the only thing, right? R is a constant, so that's not going to change. So we can also use this equation to determine a K at a new temperature when we know the activation energy. So if we know the activation energy, and we know the K at one temperature, and we change to another temperature, we can solve for K2, right? So let's take a look at a practice problem. Again, our equation. Here's the scenario. First order reaction has a rate constant of 2.45 times 10 to the second per second at 25 degrees Celsius. What is the magnitude of K at 95 degrees Celsius if the activation energy is 55.4 kilojoules per mole? So first things first, let's identify what they're giving us in the problem, right? So they give us our first K. They give us at that first temperature. They want K2. We're trying to solve for K2 at a new temperature that they give us, and we know the activation energy. So now let me break this apart a little bit because I'm interested in K2. So it might be helpful to split up those things. So I get ln of K1 minus ln of K2 equals that whole other side. We haven't done anything to that other side. So now I'm going to want to get ln of K2 by itself. So I do a little algebra, I rearrange, and I get ln of K1 minus EA over R times 1 over T2 minus T1, right? So I added K2, ln of K2 to both sides, and then I subtracted what was on the right side to move it over. So now get rid of the natural log. So I get K2 by itself. Well, I got to put the whole other side to the base of E. And I also need to note that the temperatures, they need to be in Kelvin. So the temperatures they gave me in Celsius, I need to convert to Kelvin by adding 273. So my T1 is 298 Kelvin, and my T2 is 368 Kelvin. So now, again, put the whole side to base E. We get rid of the natural log. We got K2 equals E to the ln of K1 minus EA over R times 1 over T2 minus 1 over T1. So now I just plug and chug. I know all of these values except for K2, so I plug them all in. And I'm sorry, I'm running out of room, but I plugged it all in. ln, this is K1, minus, now something to watch for is sometimes EA is given in kilojoules per mole, and typically our R is usually given in like joules per mole. So you want to make sure that you fix it. You can either make the activation energy in terms of joules, or you can make the R in terms of kilojoules, but you want to make sure that their units are the same in the equation. So I went the route of converting 8.314 joules per mole to 0.008314 kilojoules per mole Kelvin. So just plug and chug, and then you get your answer. K2 equals 1.72 times seconds to the minus 1. And if you take a look, what happens to the units? So, well, I got kilojoules per mole divided by kilojoules per mole Kelvin. So the kilojoules per mole cancel out. I'm really just left with Kelvin because it's 1 over Kelvin in the denominator. And then, hey, this 1 over the stuff is essentially 1 over Kelvin for the units. Kelvin cancels out. I'm left with per second. So that's how you do that. So summarize. Explain chemical reactions in terms of collision models, interpret corresponding potential energy diagrams, and use the Arrhenius equation. Hopefully you can do that. If not, I'm sorry. Goodbye.